is eta kk partial h44 partial qk. These guys are diagonal, right? Okay, very good. So we're ready. So our equation, which was waiting for us, qk double prime plus gamma 4k q4 prime squared is 0, will give us now, I will get this guy here, qk double prime equals negative 1/2 eta kk partial h44 partial qk, k equals 1, 2, 3, and for the 4 thing, which is q4 prime double prime, this is t double prime, right? If you substitute here q4, again everything vanishes with q for the time. So this is indeed 0. So if the double variation of time is 0, so t prime, the rate of change of time with respect to the uniform thing, is constant. So time runs uniformly. This is Newtonian mechanics, right? Time runs uniformly. That's okay. Let's focus on the meat here. Oh, we have actually q4 prime squared. So qk double prime squared. So this is what? This is what? Can you tell me what is this? What do you mean by q4 prime? What's q4 prime? Rate of change of time. So dt by d tau squared, right? And this guy is dqk by d tau squared. So the d taus, we will get them to write them in function of time. Now this is derivative with respect to time. This is negative 1/2 partial h44 partial qk, right? And I have the eta kk. But actually the eta kk for 1, 2, 3, this is unity. This is unity. This is the equation that we arrived, which reads as, I guess this is positive, right? Yeah, this is positive. So this is positive. 1/2 partial h44 partial any coordinate, this is the nebula. So if you compare with the Newtonian mechanics equation, Q double dot comes from the potential of the gradient for potential. Now you get your Riemannian metric kind of thing. This is simply -2 of the potential. So the entire Riemannian metric thing is just eta 44 plus this guy. Eta 44 is actually -1. Negative c squared, so if you normalize by c, you get -1, -2 v, and this is negative g sun. I'm sorry, negative g gravitational constant m sun over r, right? So from the potential, from the gravitational potential energy, gravitational potential, from the gravitational field of the sun, you can modify your space. This gives you what? This gives me G44, the element 44 in the matrix, right? So it gives you Christoffel symbols. It gives you the curvature of your space. I'll just add this picture. Hopefully it doesn't. Well, okay, that's okay. Yeah. Will it ruin everything? Well, I did it. Oh, no. Here it is. Yep. Very good. Okay, please. Wow. No, it's okay. See? Now I lost control on it. No. I don't know how to. Anyway, I think you have the idea. But this is what I wanted to show. The sun embeds in the space-time, it bends it. And we indeed got this curvature, the Riemannian metric or Christoffel symbol, based on the gravitational field, based on the mass of the sun. The mass of the sun is in the equation. We're done, but I mean, if you like to leave, but I like to give you a summary here for how the science is really accumulative. This is math, mechanics, and physics. And they interfere, of course. So this is, I will start with, you can start all over, but I will start with 1842, the work of Jacobi. Jacobi wrote down the principle of least action as a minimization of length element, ds squared. 1854, Riemann geometry. 1869, Christoffel symbols. 81, and 87, Michelson-Morley experiment, right, that we talked about today. 1887 also, Voigt transformation. I guess 1889, this is Darboux book on geometry of surfaces, where he wrote clearly the geometry of mechanics. 1899, the work of Ricci and Lec12. And now you can appreciate this guy, because everything is written in terms of the covariant derivative, everything is general relativity. 1904, Lorentz. This all culminated in Einstein's special relativity 1905. So this indeed made use of the Lorentz, maybe Voigt as well, because it's the same, and also Michelson and Morley experiment. But moreover, we have here in 06, 05 and 06, we have the work of Poincaré on the geometry of the Lorentz transformation. So he showed that this transformation is actually a rotation, just a rotation matrix on the 4D space X, Y, Z, and ICT. 1908, the work of Minkowski and the length element in that space, right? 1915, general relativity. You can see that how Einstein was brilliant in everything, okay? Don't need to spend too much time on that. But how lucky, because in just a few years, this is not too long ago. This is not too long ago. Look at this. Look at how fast things are moving. And indeed, without this, without the area element here, without the work of Ricci, without the geometry of mechanics, without Christoffel symbols and Riemannian metrics, and this guy is very related to that, right? These red things indeed led to the general relativity. So, and it didn't start a long time ago. It was just very fast forward. He made use of these things, and he was not even aware of the differential geometry. But it's the boldness, it's the cosmic spirit that he just walks and wondering how this world runs, how does it work? Tries to come up. This cosmic spirit we lack today, they lacked at that time. That's why they praise him. They say it's the cosmic spirit of the 17th century, Galileo, Newton, and these guys. So he had that spirit. But like I said, it's just these tools, making use of these tools. And here's the general relativity that we're celebrating until, last month we got the black hole picture. A few years ago we got the gravitational waves. I didn't talk about the Mercury enigma. There was no time. You can see it in the photo. Thank you. See you next time.